My name is Alisha and I am going to give you the presentation on topic serializability. What is serializability? Its basic assumption is each transaction preserves database consistency. The serial execution of a set of transactions preserves database consistency. A schedule is serializable if it is equivalent to a serial schedule. There are two types of serializability. First is conflict serializability and second is view serializability. There are three simplified views of transactions. First is we ignore operations other than read and write instructions. Our simplified schedules consist of only read and write instructions, and we assume that transactions may perform arbitrary computations on data in local buffers in between reads and writes. So, before seeing what is conflict serializability, we will first see what are the conflicting instructions. So, there are four types of conflicting instructions, which include read-read, read-write, write-read, and write-read. So, these are the four conflicting actions. Then, intuitively, a conflict between I and J forces temporal order between them. If I and J are consecutive in a schedule and they do not conflict, their results would remain the same even if they had been interchanged in the schedule. So, if a schedule S can be transformed into a schedule S dash by a series of swaps of non-conflicting instructions, we say that S and S dash are conflict equivalent. And if a schedule is conflict equivalent, then we say that it is conflict serializability. So, schedule, as we see in this diagram, schedule 3 can be transformed into schedule 6, a serial schedule where T2 follows T1 by swaps of non-conflicting instructions. That is, here we can see that read on A is performed by T1 and after that read on A is performed by T2. Same in schedule 6, read on A is first performed by T1 and read on A is last performed on T2. So T1 to T2 is being processed here. Therefore, we can say that they are conflict serializable. View serializability. Let S and S dash be two schedules with the same set of instructions. S and S dash are view equivalent if the three conditions are met for each data item Q, in which first is if the schedule S transaction T reads the initial value of Q, then in S dash also Ti must read the initial value of Q. If in schedule S transaction T executes read on Q and then value was produced by transaction Tj, then in schedule S dash also transaction Ti must read the value of Q that was produced by the same write on Q operation by Tj. And the last is the transaction that performs the final write on Q operation in schedule S must also perform the final write on Q operation in schedule S dash. So, as can be seen, view equivalence is also purely based on reads and writes alone. A schedule S is view serializable if it is view equivalent to a serial schedule. Every conflict serializable schedule is also view serializable. Below is a schedule which is view serializable but is not conflict serializable. In this we can see that read on Q is performed and then by transaction T4 write on Q is performed. So this is one conflicting action. Again, the write on T4, write on Q is performed by transaction T4 and again write on Q is performed by transaction T3. And as we can see that the cycle which we are cycle is forming here, so we can say that it is not conflict equivalent. So if the transaction is not conflict equivalent, we cannot say that it is not view serializable. We have to check for view serializable, and for it we first check for blind writes, and if there are any blind writes in the schedule, then we further check for it that it is view serializable or not. So the schedule below produces same outcome as a serial schedule T1 T5, yet it is not conflict equivalent or view equivalent to it. Determining such equivalence requires analysis of operations other than read and write. So, testing of serializability considers some schedule of a set of transaction T1, T2, Tn Precedence graph is used to test for the serializability. It is a direct graph where the vertices are the transactions. We draw an arc from Ti to Tj, the two transaction conflict, and Ti accesses the data item on which the conflict arose earlier. We may label the arc by the item that was accessed. In this example, we can see that the cycle is forming, so we can say that it is not conflict equivalent. In this schedule, we can see that there are various conflicting actions from which we are getting this precedence graph, and from this precedence graph we see that there is no cycle forming here, that is the graph is acyclic. So we can say that it is both conflict equivalent and view equivalent. So test for conflict serializability. A schedule is conflict serializable if and only if its precedence graph is acyclic. Then cycle detection algorithm exists which take order of n square where n is a number of vertices. If precedence graph is acyclic, the serializability order can be obtained by topological sorting of a graph. In the diagram given in this slide, from if A is the cycle given, if A is a precedence graph, from it we can derive various topological orders. The first topological order that can be derived from A is given in diagram B, and the other topological order that can be taken out from A is given in figure C. So test for view serializability. The precedence graph test for view conflict serializability cannot be used directly to test for view serializability. The problem of checking if a schedule is view serializable falls in a class of NP-complete problems. However, practical algorithms that just check some efficient conditions for view serializability can still be used. The other kind of serializability is distributed serializability. Distributed serializability is the serializability of a schedule of a transactional distributed systems. Such system is characterized by distributed transactions in a general sense depending on computing environment and possibly network nodes. A distributed transaction comprises more than one sub-transactions, local sub-transactions, that each has states described above for a database transaction. Atomic commit protocol to reach consensus among its local sub-transactions on whether to commit or abort. So, distributed serializability is a major goal of distributed concurrency control for correctness. It is used in various things like internet, cloud computing, grid computing, and small portable powerful computing devices. The need for effective distributed serializability techniques to ensure correctness in and among distributed applications seems to be increased. Thank you.